So, hi everyone, and no. I think it should be the sounding. Oh yeah, you so okay. Yeah, I think that works. We can't hear Sammy is echoing. Okay. So after a few technical issues, welcome to another series of the 8:30 seminar. Today we have Dr. Juliane Dannberg from the University of Florida. And Juliane did her PhD in geophysics at GFZ at the University of Potsdam, where she looked at the dynamics of mantle plumes. Following her PhD, Juliane was postdoctoral research associate at Texas University. She also did a postdoc at Colorado State University and was an assistant project scientist at the University of California, Davis, and was a visiting scholar at the University of Cambridge here in the UK. She's currently based at the University of Florida, where she's an assistant professor at the Department of Geological Sciences. Juliane is a fellow geodynamicist, so yes, there is more than me around, and is one of the main developers of the Mantle convection code aspect. In her work, Juliane develops computational and mathematical models of the Earth's interior, which helps us to understand how the Earth's surface evolved through time. And she's interested in processes that cause rocks in the Earth's interior to melt, the migration of the generated magma towards the Earth's surface, and how these processes are connected to the formation of oceanic islands and other forms of volcanism. So in today's talk, she will be discussing how subducted material is recycled through the Earth's interior and how this reaches the surface again as part of volcanic eruptions and ocean island formation. And with that, I leave the floor to Juliane.
Yeah, thank you. And well, thank you for having me here to talk about my research. So hello, everyone. I will talk about subducted slabs, mantle plumes, and the plate tectonic cycle. And sort of before I go into more detail, I want to say a bit about, like why that is something that we should care about at all. So like many recent studies have shown that plate tectonics and mantle convection are basically two parts of the same connected system, where plate tectonics is just the surface expression of mantle convection, and then as these plates are subducted down and the subducted slabs go down into the mantle, that's what's providing the major driving force for the motion of the plate at the Earth's surface. And it's important to understand this coupled system because on the one hand, many of the Earth's biggest natural hazards, like volcanic eruptions and earthquakes and tsunamis, they occur because of plate boundary processes. But then on a long time scale, plate tectonics also provides a means for cycling of elements such as carbon through the Earth's deep interior, and that has kept the temperatures at the Earth's surface in a range suitable for life throughout geologic history. And so, well, of course, there are many observations that can tell us about mantle convection, plate tectonics. But if we understand, if we want to understand what these observations mean, then we have to connect them to what happens in the Earth's deep interior. But the problem with that is that the Earth's deep interior is mostly inaccessible. And just to illustrate that, I have this plot here that shows us what data we have. And most of the data we have are where this green dot is. So that's at the surface of the Earth and at the present day. We can go along the horizontal axis here back in time because we have the rock record that tells us how the Earth's surface has looked like in the past. We can also go along this vertical axis down into the Earth's interior because geophysical data tell us how the Earth's interior looks like today. But still, that means there's this huge part of the diagram where we have very little information available. And so we can use modeling to connect these data points that we do have to tell us how the Earth's interior looked like in the past. And so the type of modeling I use is geodynamic modeling, as Anthony had mentioned. And so specifically, the questions I want to look at today is sort of what drives the motion of the tectonic plates at the Earth's surface. Then as these plates are subducted down into the mantle, what happens to them, and specifically what happens to the crust, the oceanic crust of these plates, and can it accumulate at the common boundary? And then if it accumulates there, can it brought back to the surface again in mantle plumes? And can it explain some of the observations we have of ocean islands? So I'll start with the first topic, that's understanding the forces that drive plate tectonics. And all of the models I will show, they were done by my postdoc, which is Xena, shown here. And so like by understanding what drives plate motions is an important topic. So of course, there were lots of other people who had looked at this as well. And this slide shows 4 different geodynamic models where the modelers try to reproduce the present-day plate motions in their geodynamic model. And so we can see some of these models show sort of with these arrows how their predicted plate motions from the model, how they compare to the observations with these arrows. And so we can see in most places they agree relatively well. So both of the arrows have like sort of similar direction. So that means we already have a reasonably good understanding like what causes the plates to move in that specific direction. But on the other hand, we can also see all of these models use the same geometry of the plate boundaries, so shown here as these red lines or over here. And so that means we don't know how the geometry of the plates affects the plate motion. And another thing that's important about these models, so to predict the plate motions, the model needs to assume something about the internal density structure of the Earth. And that usually comes from a seismic tomography model. So it's important to think about like what seismic tomography model do we use here? And this slide is to illustrate like why that can be really important. So this shows a slice through 2 different seismic tomography models at the location shown here. So it's through the Andes subduction zone where the Nazca plate is subducted. And so the colors here show the seismic velocities, where blue is fast and red is slow. So red would be high temperatures, blue would be cold temperatures. And on the right is this S40 RTS model, which is what many other of these geodynamic models have used to predict their density structure. And on the left is a more recent model, the LNNL model. And we can see if we look at sort of this subducted plate that's going down into the mantle here in the model on the left, we clearly see this blue cold structure going down. Whereas here on the right, we see some blue blocks, but it's not really like a slab that's going down here that's connected to the plate at the surface. And so, right, you might imagine that this would give you really different driving forces for the plates at the surface. And so what we did was we used a more recent version of this model, the global tomography model from Simmons et al. And then we converted the seismic velocities in that model to temperature to give us the temperature structure in our geodynamic model below 200 kilometers depth. And so above that depth, we have other observations that sort of give us a better idea of what the temperature is, like the heat flux in the continents, or we know the age of the oceanic plates, and we know where trenches are, so where subduction zones are located. So in the uppermost part of the model, we use those other observations to constrain our temperature. And so we combined those 2 models to give us the temperature structure for our whole mantle, and then converted that to density and to viscosity. And so the viscosity determines how easily we can deform the Earth's mantle. And because that's such an important parameter, I want to go into a bit more detail of how we set that up. So on the left here, what we see is the viscosity profile, so how the viscosity changes with depth, which is a profile from Dannberg and Calderwood. And in addition to that, we also have lateral viscosity variations. On the one hand, caused by this temperature I showed in the slide before. And on the other hand, we prescribe weak plate boundaries. And so we reduce the viscosity in those plate boundaries. And so all of that combined gives us our viscosity structure. But there are large uncertainties in each of the different parameters that go into this viscosity structure. And so what we do in the study is we vary the 2 parameters that we think are most important for the motion of the plates. So on the one hand, it's the viscosity of this layer in the viscosity profile, so the viscosity of the asthenosphere, because that determines it determines the friction between the plates and the asthenosphere below, so how easily the plates can slide across the mantle below. The other parameter we change is the viscosity of these weak plate boundaries. So we change the friction between the plates, or how easily the plates can slide past each other. And then we look at sort of which of these combinations of viscosities will give us the best fit to plate motions. And then we ran all of these models with the aspect code that I'm also developing. And because these are like global models and we need to also resolve the plate boundaries, we had to run them in really high resolution. So we needed to run them on 5,000 compute cores and NSF's biggest supercomputer on Terra. So there are 1 billion sort of points where we have to find the solution in this model. So let's look at some of the results. So here, each of the images is one different model, where on the x-axis, what changes is the plate boundary viscosity, so it increases towards the right. On the y-axis, what changes is the asthenosphere viscosity. And then the color in the image shows us how fast the plates are moving compared to the observed plate motions. So if the colors are red, our plates are moving too fast. If the colors are blue, our plates are moving too slowly. And if the colors are whitish, then they have approximately the right velocity. And so we can see one parameter that has a really big impact is this plate boundary viscosity. And there seems to be sort of one value where the fit is reasonable. And then if the viscosity is too low, the plates are just moving too quickly. If the viscosity is too high, there's too much friction and the plates move really slowly. The asthenosphere viscosity also has an impact. And we can see that especially the continental plates that have these fields going into the asthenosphere, they become really slow if we make the asthenosphere viscosity really large. But so then, this is sort of looking at it in a qualitative way, but now we also want to quantify, well, which of these models actually has the best fit. And we used 3 different criteria to compute the fit. The first one is the direction of plate motion, where we basically said we compute an angular correlation. And if our plates move in exactly the same direction as the observed plate motions, then we get 100% correlation. If it's 90 degrees off, we get 0. And if they move in opposite direction, we would get a negative value. And so here on the left, we see like 4 these different models that we ran. Again, the 2 axes are plate boundary viscosity and asthenosphere viscosity. Like the color of the dots shows us how good this angular correlation is. So the more yellow, the better the fit. The other 2 criteria are the speed residual, so the difference between the speed of the plates predicted by our models and the speed in the observation. So that's just the difference between the 2 that only looks at the speed and not at the direction. And so that's in centimeters per year, and the lower the number, the better the fit. And so that would be the more whitish colors here. And the last one is the root mean square residual that combines both direction and speed, where we just say we take the difference between the sort of vector of modeled and observed plate motions and then integrate it over the whole model. And so that gives us an overall fit, also in centimeters per year. And also, again, lower values and whitish colors are a better fit. And so we can also see for these last 2 criteria, there's always this sort of sweet spot where we get the best fit. And if the plates are moving too slowly, then we get a bigger residual. And if they're too fast, we get a bigger residual. If the plates are moving too slowly, we also get a bigger residual. But I said, well, we want to understand how the plate boundary geometry affects the plate motions. And so far, all of the models I've shown, they've been using the same plate boundary geometry that everyone else has been using as well. So what I want to look at next is like what other plate boundary geometries we might use. So the first one I show here, that's the plate boundary geometry from Nouvelle. So that's the model from more than 30 years ago that all of the other models have been using. Here on the right, we have a more recent model from Berg 2003. And the difference is that this has some more smaller plates. The third scenario that we're using is the one in the bottom left, where we have the same plate boundaries from this Berg model, but we only have them in the oceans and we don't have plate boundaries in the continents. And in the bottom right, we have sort of the same scenario as in the bottom left, but in addition, we have plate boundaries in the continents as well, but they come from the global earthquake model. So these are based on seismicity. And so they are only in the crust and they don't go through the whole plate. And we can see that they are sort of more distributed in all of these regions here where basically seismicity is detected. And so now we ran models with all of these different geometries of the plate boundaries, and that's what's shown here. So basically each column is a different plate boundary geometry. And again, the x-axis is plate boundary viscosity, the y-axis is asthenosphere viscosity, each dot is one model, and those are our 3 different criteria for evaluating the fit of the model. And so the first thing we can see for the direction of the plate motion basically all of the other models do better than the Nouvelle model. So the yellow colors are better correlation. And it looks like if we have higher plate boundary viscosities and lower stratosphere viscosities, we get a better direction of it. For the speed and the root mean square velocity residual, we also see all of these sort of, again, have the sweet spot where we get the best fit. And it's a bit hard to tell sort of which model gives us the best fit. So we just looked at the numbers and now compared sort of, like in this slide, I compare the best fit model for all of the different geometries. So this is the best fit model for the Nouvelle plate geometry. And in this image, the arrows, so the blue arrows are our predicted plate motions. The black arrows are the observed plate motions. And the color shows the pointwise residual of the velocity. So if the colors are white, we fit the plate velocities well. And if the colors are like blue or green, then we don't fit the velocities well. And so we can see for this Nouvelle model, we fit the Pacific plate really well. So here in the center, but then many of the other plates don't fit that well. For this bird model and the bird model only in the oceans, we don't fit the Pacific plate well. And so, but then some of the other plates are fit better. And for this model that includes the global earthquake model plate boundaries, we fit the Pacific plate reasonably well, but we can see that many, especially the continental plates, they are fit quite well, and only some of the smaller plates don't have a good fit. And so if we quantify these numbers of which model actually does have the best fit, so if we look at the angular correlation, if we compare the 4 different models, then we again see the Nouvelle model has the worst fit, and the model from like all of the other models do better, and they do similarly well with this global earthquake model having the best overall fit. If we look at the root mean square velocity residual, where like lower numbers are better fit, again, the Nouvelle model doesn't do that well. These two bird models do a little bit better, and the model in the bottom right from the global earthquake model, that's the one that also overall has the best fit. So sort of what we can, like what do we learn from this about the plate boundary structure in the Earth? So on the one hand, like that this model has the best fit tells us the plate boundaries don't have to be close to give us a good fit. So that's something that like many geodynamic models assumed, that sort of you need a plate boundary model that has these closed boundaries that encircle the whole plate. But those models at the bottom actually give us a similarly good fit, or even a better fit. And then the fact that this model is the best one tells us the sort of the structure of the plate boundaries is different in the continents compared to the oceans. So in the oceans, we have these plate boundaries that are discrete and go through the whole plate, whereas in the continents, we have these sort of more distributed zones of like zones that are easy to deform, and that only go through the crust and not through the whole plate, and gives us more distributed deformation. So that was the first part about like the plate motions and what drives the plate motions. So in the second part, I want to look at what happens when these plates are subducted down into the Earth's deep interior, and specifically what happens to the basaltic crust, and if it can accumulate at the cometal boundary. And all of these models, they were run by my former postdoc here in Kotalia. And the sort of the motivation behind this is that we know that subducted slabs, as they move down into the mantle, they introduce heterogeneity. So we know they have a basaltic crust and they have a hard spaghetic lithosphere. And the question is, well, what happens to these materials on long time scales? And so mineral physics sort of can give us some idea, because we know the basaltic crust is denser than the rest of the mantle near the cometal boundary, and the hard spaghetic lithosphere is less dense, and so the crust might sink and the lithosphere might rise. Another idea we get from seismic observations, because they show these two zones of reduced shear wave velocities near the cometal boundary, and some people have speculated, well, maybe these are piles of dense material, maybe this is this crust that accumulates in these piles. And we also have observations from geochemistry that tell us ocean island basalts have a different composition than mid-ocean ridge basalt. They contain some recycled materials, so maybe those are plumes carrying material from these piles back towards the surface. And so we want to better understand what happens to the basaltic crust. And one really important parameter for that is the mantle viscosity. So how easily can the mantle deform, and how easily can the crust separate from the rest of the slab. And we know that this viscosity changes in the lowermost mantle because there's a phase transition from bridgmanite, which is the biggest sort of the major phase above the cometal boundary, and then it transitions to post-perovskite, which has been suggested to be much weaker than bridgmanite. So it might be like a factor of 1,000 easier to deform than bridgmanite. And so we wanted to look at how does this transition, when the material becomes really weak, how does this affect how easily the basalt can separate from the slab. And again, there were other people who had done this before. And so here I showed two different studies. The study on the left is from Lee and McNamara. And so here the colors, the blue and red colors show temperature. Again, like red is hot, blue is cold. And then these green colors here, they show the basaltic material. And these are two different models. So the one at the top is one where post-perovskite does not affect the viscosity. And the one at the bottom, post-perovskite, is easier to deform. And so what they concluded is if we have this viscosity, the lower viscosity of post-perovskite, we get less basalt to accumulate at the common boundary. So we can also see that here there are more of these green piles here and less down there. Then the model on the right is from Nakagawa and Tekley. They looked at the same question. In this case, the color shows the chemical composition. So the more red, the more basalt. And again, the model at the top is post-perovskite does not affect the viscosity, and at the bottom, post-perovskite is easy to deform. And they find exactly the opposite. So they say, well, if we make post-perovskite weak, we now get more of these red piles at the common boundary, and so we get more basalt to accumulate. And so that means it's still totally unclear what the effect of post-perovskite is. And we need a more systematic study to better understand what actually, why are these so different and what causes this effect. And so what we did was we set up a geodynamic model, again, an aspect. We only looked at the lowermost 1,500 kilometers of the mantle. So as shown here, it's a 2D model and sort of a cylinder. And we made the side boundary conditions periodic so that we could basically get the whole Earth. Then the top boundary of the model is open. And so material can flow in freely, but we prescribe the position of two slabs that come into the model. And we prescribe those both in terms of temperature, so they are cold, and we prescribe the composition. And specifically, we assume sort of the mantle is made of pyrrolite, the slab is made of a basaltic crust, and then a hard spaghetti lithosphere. And then we compute all of the material properties with the mineral physics database and with the thermodynamic software Hephaestus. It gives us like the density and all of the other properties. And then we use aspect in high resolution to run these models. And because we need to resolve this really thin crust, so we had 11 million particles that track this composition. So let's look at some of the model results. So here we see two animations of two of these models. In the model at the top, that's one where post-perovskite does not affect the viscosity. In the model at the bottom, post-perovskite is easy to deform. The colors again show the temperature, and then the green, this green material, that's where the basalt is. And we can already see that these models are quite different. So things seem to happen faster in the model here at the bottom. And we can see it seems to be like this green material seems to accumulate much faster near the common boundary compared to the model over here, where everything just happens more slowly. But we said we wanted to study this in a more systematic way. So we again vary two different parameters in this model. The first one is how weak is the post-perovskite phase, from same as bitumenite to being a factor of 1,000 weaker. The other parameter we varied is the thickness of the crust and the whole slab that's coming in at the top. And so you might ask, well, like we know what the thickness of the oceanic crust is at the Earth's surface, why is that something we would vary? And so the reason is, as the slabs go down into the lower mantle, the viscosity increases, and so they have to slow down. And so you could think if they slow down, they sort of are squeezed together, and so the crust might become thicker. Or also earlier in the Earth, we might have a different crust thickness. And so we vary the crust thickness between 10 and 40 kilometers. And then we let these models run for 400 million years, and we track at how much basalt do we have in the lowermost 300 kilometers of the mantle. And so here we see sort of screenshots of the model after these 400 million years, where each image is a different model. And again, along the horizontal axis, what changes is the post-perovskite viscosity, with it becoming weaker towards the left, and on the right, it's the same as bitumenite. And on the y-axis, what changes is the crust thickness from 10 to 40 kilometers. And we can see that we get quite different results for different models. So some of them accumulate a lot of basalt, and some of them accumulate very little basalt. So let's quantify this. These are like the same models. Each model is now a dot, and the color and size of the dots represents how much basalt has accumulated at the end of the model run. And so we can see like the two parameters both affect this result. So if we look at the crust and thickness, the bigger the crust and thickness, the more basalt we accumulate. But for the post-perovskite viscosity, it's a little bit more difficult. So if we start from the same viscosity as bitumenite and then go towards the left, we first here accumulate more basalt. But then if we go even further towards the left, we here accumulate less basalt. So something is apparently changing in these models. So to understand what's happening here, let's look at sort of the images of the models again. This is an image of the animation we looked at the very start, where sort of the viscosity of post-perovskite is the same as bitumenite. Then this is the second animation where post-perovskite is a factor of 100 weaker. And so if we compare the two, we see that in this image, it's much easier for the basaltic material to be separated from the rest of the subducted slab. And so that's why it can accumulate at the common boundary more efficiently. But the other thing we can see is also that the lower we make the post-perovskite viscosity, the more vigorous plumes we get in these models. So if we reduce the post-perovskite viscosity even further, we now get this really strong plume, and it drains all of the basaltic material, so all of this green material back towards the surface. And so that's why it can't accumulate at the common boundary anymore. So we have these two competing processes that one, the weak post-perovskite facilitates the separation of the basalt from the slab, but it also facilitates stronger plumes, and so it takes away the basalt from the common boundary again. And so to accumulate a lot of material, we need the segregation to be big, but the entrainment to be small. And so where the change from one being dominant to the other being dominant occurs also depends on the crust of thickness. And that's what caused the differences between the previous studies. So the study from Nakagawa and Tekle, they had a thick crust. And so they went from here to there in the diagram. And so they saw we get more basalt to accumulate at the common boundary. The study from Lee and McNamara, they had a thin crust. So they went from this space in the diagram to over here. So they saw less basalt accumulating. So the studies were both right. They just looked at different parts in the parameter space. And so then, of course, it might be interesting to ask, well, which of these models actually explains the volume that the volume of basalt that we think is at the common boundary today. And I mean, on the one hand, we don't really know what that should be, so I have to make a lot of assumptions here. So what I did was, on the one hand, I said, well, the rate of accumulation of basalt in my models stays the same for 3 billion years. So I extrapolated it over time, so that's probably not the case in the Earth. And I also said, at the moment, the LLSVPs make up at least 3% of the volume of the Earth. And so that of course also has an assumption that they would all be basaltic, which is probably also not true. So it's just sort of a rough guess what would be the right amount of basalt. But if we make these assumptions, then only those three models in this triangle, they would accumulate enough basalt to reproduce the present day LLSVPs. But of course, since they might not be 100% basalt, some of the models that are close to that volume might also be realistic for the Earth. So what we've learned is basically, if post-perovskite is weak, that can both facilitate or it can hinder the accumulation of basalt at the common boundary, and it depends on the viscosity of post-perovskite and the crust of thickness, because if it's a little bit weak, then it just facilitates the separation of the basalt from the slab, and more basalt can accumulate. If it's really weak, it produces stronger plumes, and that entrains more basalt away from the common boundary, and then basalt can accumulate less. And where we go from one to the other depends on the crust of thickness. So now in the last part, I want to look at, well, maybe do we see of some of this material that accumulates at the common boundary back being entrained towards the surface in ocean islands? And so I want to look at how convection simulations might explain compositional heterogeneity of ocean island chains. And this is work I did with René Gassmer. And so I talked about these LLSVPs. So here I actually wanted to show an image of them. So these are these zones of low seismic velocities just above the common boundary. And so if we now take the locations of ocean island basalt and sort of plumes today and large continuous provinces and project them down towards the common boundary, so that's what these green and yellow dots are, then we see that they are like either like in the area or near the edges of these LLSVPs, so at the around these red regions. That's one observation. The other observation is that many of the ocean island chains, they have these parallel volcano chains with different chemical compositions that run parallel to each other. So the most famous one is the Loa and the Kea trend in Hawaii. but this has also been observed for Society and Samoa and many other ocean islands. And so these trends also seem to align with the LLSVPs, like with their margins. And so because of these observations, that has led to the idea that, well, maybe if the LLSVPs, if they are reservoirs of dense material, and the plumes, like maybe they are plume generation zones and the plumes rise from their edges. And so we could think about it like this, that if a plume rises here on one side, it entrains the material from the reservoir. On the other side, it entrains the normal mantle material and it rises towards the surface. And we get these two different compositions in the tracks that run parallel to each other. And so, well, then the question is, well, is that actually what happens in numerical models? And so this is a study from Jones et al., where they looked at, well, if we have a plume here rising from the edge of this reservoir, with the reservoir material being red, what will happen? And they find that, well, sort of we entrain the material on one side of the plume. This is how it would rise towards the surface, and the plume conduit, if we make a cross-section through that, it would look like this. So it would be bilaterally zoned, and so we might think, well, that could explain these observations that we have at the surface. But so this is if the red material has the same density as the rest of the mantle. But what we just looked at is, well, if we have basaltic material, we would expect it to be dense. If it's been down there for a long time, it has to be dense, otherwise it would immediately rise. So if we take that into account in the models, we get the scenario at the bottom, where if the red material is dense, it will accumulate, it will pool at the base of this plume, and it will be entrained here in the center of the plume. And so then a cross-section would look like this. And so that would no longer explain these two trends next to each other. And so we had that means it's still unclear how do we get these parallel trends. And so we had the idea, well, maybe we can't look at the plume alone. Maybe we also have to look at subduction and the subducted slabs and how they influence this process. And maybe that can make a difference. And so we wanted to test this also in numerical models to see if that actually would have an effect. So let's start looking at a simple model where we only look at the lowermost part of the mantle. These are 3 different models where, like, from the top to bottom, there's always a subducted slab coming in from the left, and the influence of the slab increases from top to bottom, so it just comes in with a faster velocity. The red and blue colors, again, are temperature, and then these outlines here, that's the reservoir, so the different composition. And we can see in this model at the top, where the slab is so slow that we don't even see it in this image here, the plume rises from the top of this reservoir. And if we do a look at the cross-section through the plume conduit and look at the temperature, which is shown here in red, and the chemical composition, which is shown here in black, like they are symmetric. The highest temperature and the highest amount of material entrained from the reservoir, they are in the same location. But the bigger the influence of the subducted slab, the more asymmetric the whole process becomes. So here we see as the slab comes in, it makes the plume generation zone asymmetric. So the plume here rises from the edge of the reservoir. And if we look at the cross-section, the point of the highest temperature is further towards the left here compared to this point here of the highest amount of material entrained from the reservoir. So like this idea seems to make a difference. The subducted slabs do make this process more asymmetric. And so we wanted to study this in more realistic 3D simulations. So we used an octant of a sphere of the Earth's mantle to run our simulations, again in aspect. We assumed that the mantle is a mechanical mixture of Hartsburgite and mid-ocean ridge basalt, and then we assumed that this reservoir here would be made up of 100% basalt. And we used again a mineral physics database in the thermodynamic software Perplex to compute the material properties. And then as the boundary conditions for this model, we ran a global model that at the surface had a plate reconstruction prescribed as the boundary conditions. And that's because then we would get the subduction zones in the same locations where they were in the Earth's past. And so we would get them in the right location to sort of affect these chemical reservoirs. So let's look at one of these models. So here again, the blue outline is the cold temperature, the orange outline is high temperature, and then the green colors show the reservoir. And we can see that here's a slab coming in from the left. And so then as it reaches the cometal boundary, it pushes material against this pile and it triggers this plume to rise. And if we look, we can already see that this seems to be asymmetric. So there's more of this green material in the right half of the plume And then sort of the left side of the plume is orange, so it's hot, but it doesn't have as much of the material from the reservoir. So we wanted to see under which conditions does that happen, when do the plumes become asymmetric and how much. And so we defined a plume asymmetry number based on, so we did a cross-section through the plume conduit in 500 kilometers depth, and then looked at what's the overlap between the region of the highest temperature, so that those are the colors from dark red to white, and the region of the highest amount of entrained material, so those are these blue contours. And we can see that there are some plumes that are not very asymmetric. So if we look at this one, for example, the highest temperature and the highest amount of material are basically in the same location. So that would get a really low asymmetry number. In this case, it's 0.04. But there are also plumes that are more asymmetric, like the one in the bottom right here, where this is the part with the highest temperature, but over here is the part with the highest amount of entrained material. So that gets a bigger asymmetry number. In this case, it's 0.88. So these numbers are between 0 and 1. And so now we can plot these asymmetry numbers versus different model parameters. So this is what's shown here. The model parameter we use here is the plume excess temperature, how much hotter are our plumes than the rest of the mantle. And on the y-axis, we have this asymmetry number. And so one thing that we can see is there seems to be a trend in the sense that only plumes that are hot are asymmetric. So if the plumes are not that hot, then none of them are asymmetric. But there are also plumes that are hot and that are not particularly asymmetric. So this is not the only factor that influences the plumes. And so this is where our subducted slabs come in. So in this plot, it's sort of a similar type of plot, but now the x-axis is the angle between sort of the margin of our reservoir and the velocity in the lowermost mantle. So how, like in which direction the slabs are moving. And so if this angle is large, that would be, so it's sort of flow in the lower mantle towards the reservoir. So if here the reservoir is shown in blue, the normal mantle in white, and then these arrows show where the material is flowing. So that would be a high angle, or the flow could be sort of along the reservoir. So something like this, and that would be a low angle. And again, we can see we only get asymmetric plumes for the right part of the diagram. So only if we have a large angle, if the piles, sort of the subducted material is flowing towards the pile and not along the pile. And so sort of our interpretation of this is what happens is we get these asymmetric plumes if we have subducted slabs that go down into the mantle. If they push material against our reservoirs, they make the plume generation zone asymmetric. And then as the plume rises here, it can entrain part of the material from the thermal boundary layer on top of the common boundary over here. And on the other side, it would entrain some material from the chemical reservoir. And now the question is still, well, would we actually see that in the composition of the melts? And well, so I won't talk about that a lot, but basically the idea is you can imagine that it depends on the plate motion. So if the plates are moving in this direction, right, if the plume is zoned like this and the plate moves like this, then we move the two trends on top of each other. And if we now sample them in the melting column, we just don't see any difference because we sample both of them. But if the plate moves sort of in, like here, sort of into the slide, so if the trends are like this and they move like this, and we now sample them, we would get like these two trends that run parallel to each other, and we would see different compositions. So to conclude the last part, if we consider the interaction between a subducted slab that arrives at the common boundary and the rising plume and this chemical reservoir, then we can find that plumes are asymmetric, even if the material they entrain is dense, but it only works if the plumes are hot and if there's motion of the production zones towards these reservoirs. And then it depends on the plate motion if we actually see that in the created melt or not. And so with that, we've gone all the way from the surface to the common boundary and back to the surface again. Thank you.
Juliane, do we have any questions?
I found that really interesting. I am more of a geochemist, so I'm not a modeler. But is there actual seismic data that shows basaltic slab going down to the full mantle boundary?
So there is seismic data that shows slabs going, well, at least like through the transition zone and most of the way to the common boundary. But the basaltic part of the slab is of course very thin, so we wouldn't know right? We wouldn't know if that also includes the basaltic part. We know that cold material goes down, but that's sort of the extent of what we can say.
Okay, because from a geochemical point of view, some of the plumes that you showed towards the end there, like in Galapagos, they are plumes that are geochemically thought to be undisturbed, undegassed, so from material that's kind of been at the core mantle boundary and doesn't include any recycled material. So when you talk about the type, is that something that is seen through seismic data? It's just implied.
Yeah, so right, that's still one of the big questions, like what are these pilots, right? The seismologists can only tell us they have reduced seismic velocities, and they can maybe tell us what's the P wave velocity, what's the S wave velocity. So from that, many studies have inferred they need to have a different composition because there's not a direct correlation between the reduction in P and S wave velocity. On the other hand, there are people who say, well, they don't like our data, the accuracy is not good enough, so to actually tell that. So there are still people who say maybe they don't have a different composition at all, maybe they are just hot. But if we agree they have a different composition, they might of course be lots of different things. If like there is this evidence of sort of plumes clustering around these areas, and not just the plumes today, but the plumes in the past. And so from that we infer, well, this is probably material that was at the common boundary for at least a few 100 million years. So if there's something that stayed down there, it probably is dense. But it's not clear what it is, and it's likely that it's not 100% basalt. It could be some, but it's likely that some basalt sort of, if it's subducted down, it would stay at the common boundary, but it could be some sort of primordial material. It could be something from the crystallization of the early magma ocean. We just don't know what it is. And it's also really hard to tell. And the only thing, the only observation we have is like, what do plumes bring towards the surface? Oh, I was just wondering, this is the question.
Oh. Yeah. Emma?
So I mean, right, like I think Antoinette would be the person to ask about like slab stalling in the transition zone. And so like for my models, right, I think it would have an effect on, so that it's really simplified that I said, well, I just like take the whole structure of the slab and I put it into my model at like sort of at 1500 kilometers above the common boundary, and it's still straight, right? That's not what other models show. So the structure of the slab could be more complicated. Like, right, the slab could bend, and then it would look really different. So that would be one difference. I still think for slabs, it would be really hard to entrain material or have any material separate before they reach the common boundary, just because they are so cold, and that makes them so hard to deform. But you could think about, one thing you can think about is like what happens to the water in the transition zone. So that could like be released, or like then what happens if a plume comes up? Can it like take some of that? And then for plumes, you could also think about, well, maybe plumes under certain conditions, maybe they can stall in a transition zone because of the phase transitions, or like if plumes carry this dense material, the density depends on sort of at which depth you are. There's like sort of below 660, the basalt would actually be less dense than the rest of the mantle, so the plumes might speed up, but then above that they might slow down. And so like there are like different things that could go on in a transition zone, and they could all affect sort of what, right, they could filter some of the material, some of the composition, and could influence sort of what you then would actually see at the surface.
Do rising plumes always avoid sinking slabs? Which kind of broaden that point. How fast is the plume rising? Every image you show plumes that either which may die out somewhere in the mantle, or just basically where the down the slabs.
So I would say, in general, plumes often, like in these global 3D models, plumes often avoid slabs just because of the general structure of subduction in the Earth today. And so that you have this ring of subduction zone around the Pacific, and so that means you sort of have this degree 2 structure, that you have this ring of material going down, and then you push against the piles on both sides, one below Africa and below the Pacific. And if this is where the plumes rise, then there are mostly no subducted slabs there because they are sort of in this ring around the two piles. But of course, you could imagine that, like, if, like in the Earth's past, or like if you just have a subduction zone that's above one of these piles, but you could still have plumes that hit the base of a plate. And I think one of the most famous examples where that has been argued is the Yellowstone plume, where they think, well, maybe the plume somehow tore, like either there was a slab window and the plume got through, or like tore the slab apart. And so I think there are examples where we think that has happened in the past.
I think it's also been suggested for some alternative that we go.
All these and very as long as there's any confirmation, if you like, of the idea that these events saying, well, in order to have lots of in that difficult surface, the condition is not to have that kind of feel or some hundreds of before. People say that quite a lot, but it's like kind of backed up with the screen.
So that's actually something I didn't show at all, but I also do models where I basically, so where we take a plate reconstruction of the last 1 billion years, which then of course is very inaccurate, but it sort of shows how the subduction zone locations would have changed throughout sort of the whole supercontinent cycle. And sort of what we did was we made the assumption that we have this dense material, we just put it at the base of the mantle and we look at how would it move around and would we still get plumes. And sort of the dense material still stays at the chromatal boundary, but it changes in location. So you would not always have these two like piles of hot material, but you could sort of, as you have the stable supercontinent, but you have one hemisphere where you just have continents, and then you have the other hemisphere with the ocean where you have the subduction zones. So where you have the subduction zones, you have all of the cold material at the chromatal boundary also in one hemisphere and all of the hot material in the other hemisphere. And if you are in the breakup of the supercontinent, you get something like today where you have the sort of ring of subduction zones. And if you're in the time where you assemble a supercontinent, you might have subduction zones in like random places somewhere, and then you might get a smaller scale structure where you break up your piles. So you would still always get plumes because you always have subduction zones, but they might not be in these two places, sort of in the two hemispheres. Yeah. So Wood recently discovered mineral phases like Dave Maui's impact my modeling, and do I think they are still undiscovered phases of relevance? So I don't know for the specific phase what the properties are, and so that, like, I mean, in general, any phase always affects what's the density, what's the viscosity of the material. So well, and it would also affect sort of like what's the grain size of the material. So that would always have an impact on the modeling. And the sort of the question is how big, like how much are garbage can mineral with higher So
we just have we have some mineral that's just sweeping up. So how does that just sweep? Yeah.
So like that sounds like it would mostly important if you were interested in the geochemistry of sort of if you wanted to track, right? So I've generalized this a lot, right? The geochemical data are of course like sort of different radiogenic isotopes, and I just said, well, I assume one trend is basalt and the other trend is like average mantle. So it's like, right, it's really simplified. So I haven't even taken this into account, like where would all of the trace elements go? How would they partition when I melt the material? I just basically looked at how much melt comes from melting basalt, how much material comes from melting average mantle. And so like this seems like it would be important if you wanted to track where do all of the trace elements go and where, and I mean maybe also for radiogenic heat production, if you have more of the heat producing elements go into a specific phase.
Next.
Oh. And then like for the geodynamic models, the two important properties I always looked at were the density and the viscosity. So if it's a mineral that has a really different viscosity, that would of course make a big difference because it would be easier to deform the mantle. If it has a really different density, then it would also make a big difference. And I mean, I'm not a mineral physicist, so I have no idea if there are still undiscovered phases of relevance. But like since there are more discoveries, right? While I've been in academia, there have been like new things discovered. So I mean, there's no reason to assume there wouldn't be any others. I hope that answered the question.
So I have a quick question. So going back to the plate and the geometry of the plate, did the size of the plate, so how big the plate was, did that make any difference? Was there essentially a correlation between the size of the plate and the type of geometry and the fit in terms of either the angle or the speed?
Let me go back, and you can see that there's like a very clear, like it does make a very clear difference because it's much easier to fit a big plate than a small plate. So even if you just look at sort of the best fit model here, yeah, I can make this bigger, right? You see, mostly the big plates fit really well, and then some of the small plates have a terrible fit, and that's mostly because for a big plate. But if you have some place where your subduction zone is wrong and the seismic tomography model, you integrate over a bigger area. And for a big plate, it doesn't make a big difference if there's like one small place that's wrong. But for a small plate, if there's a small place that's wrong, it might make a really big difference. So for like, and I think what's also making a difference, so like this is the Indian plate, which is wrong. So it actually also doesn't even move in the right direction. And we think that's because like, sort of here, that's a collision zone, which is tectonically a really complicated area. So it's difficult to get that right to transfer the right amount of stress from the slab to the plate. And so, but if you have a small plate and then it also has a complicated tectonic sort of region, then that's the most difficult to fit. So, and the sort of the oceanic plates are easier to fit because they are like really simpler, and the bigger plates are easier to fit.
So I guess also depending on how much the amount of subducted slabs surrounding the plate, that is the right.
Yeah.
That's why kind of it's a bit easier than
well, but the other thing is also, so if we compute the residual in absolute values, so centimeters per year, so that means your misfit gets really bad if you have a bad fit for a big plate and if you have a bad fit for a fast plate. Yeah. And so you kind of have to fit the Pacific plate to get a reasonable fit. So the best fit models are always the ones that fit the Pacific plate well, because otherwise the fit is just really bad.
And if you find, sorry, I'm not the question, but if you find any, so let's keep it straight, then that's okay. Was there anything that helped with that?
I mean, like so I didn't know about that. I mean, you can see that in different models we fitted like, well, in some of them we fitted better than in others. I think it's, yeah. I mean, the direction is sort of almost right. In this best fit model, it goes too fast, and so it depends on the viscosity, and you kind of right. So both viscosities, you make them smaller, and the plates go faster, but they affect the big and the small plates differently. Right? If you have a small plate, the ratio between the boundary and the area is bigger, and so the plate boundary viscosity makes a bigger difference. And for the bigger plate, the asymmetry viscosity makes has a bigger impact. And so you have sort of to get both of these, like you have a reasonable ratio. One other plate that I know people don't get right often is like the North American plate actually. And this, like, we don't know why it fits well, but like it just like with the models that we use, that just worked out to like move in the right direction.
Thank you.
Maybe just a quick one that I'm just more curious about here is one of the things about this GM model you mentioned is that it has these open plate boundaries. So how does that work with like when we are understanding? I mean, physically we don't have open plate boundaries. So what's being approximated there? How does that work?
Well, I mean, right, physically, so right, the plate boundaries in the continents, they would mostly be sort of origins, collision zones. And I think, right, it's like we don't know that much sort of like what's the structure of these plate boundaries. We know that they are weak somehow, but I think if we look at maps of sort of the distribution of the strain rate, they don't show up as these discrete boundaries. But if you look at the strain rate, it's also more like they're sort of distributed deformation over a bigger area. So I think that reflects the viscosity structure. I think that means that we do have sort of maybe server regions that are a little bit weak. So if we have a connected network of faults, rather than one fault that goes through the whole plate, that's just what happens if we have a collision zone and sort of fuse the two plates together. I think that's what reflects.
Okay. There are no more questions left. Thank you, Diana.
Thank you.